The next section we're going to be talking about in our class has to do with patterns, but patterns that are made by exponents rather than by adding and subtracting. So if you remember before, we saw things called arithmetic sequences and series, and that would be something like if it started with 5, then maybe went to 7, 9, etc. We said that 5 was the first term and that the terms had a common difference equal to 2. And we could even then go ahead and find a rule for this type of sequence. So we said you could find the nth term by taking the first term and adding to it the difference a certain amount of times. And it happened to be the amount of times of n minus 1, one less than the term you wanted to find. So the rule for this sequence that I'm looking at here, the first term is 5, the difference is 2, so that would give me 2n minus 2 for that quantity. I have that 5 being added to it, so I would get 2n plus 3. So this is a reminder that that's how we would write a rule for an arithmetic sequence, and that we would call the different terms. Remember, A represented a term, the little subscript next to A represented what term, and D stood for common difference. So now we're going to be looking at geometric sequences, and this is a sequence in which the ratio is constant. So instead of a constant difference, it has a constant ratio between terms, and they like to call that R. So for example, this would be a geometric sequence. Okay. 1 would be the first term, and the common ratio between terms is 2. And that's obtained by either asking yourself, what am I multiplying one term by to get to the next? Or by taking a term and dividing by the term that came before it, and that would give us 2 in each case. So when we look at this example here and they ask us, is this a geometric sequence? To confirm that it is, or maybe that it isn't, what we could do is take a term. It needs to have a common ratio if it's geometric. So remember we said you calculate the ratio by taking a term and dividing it by the term before that. Okay? And then I'm going to go ahead and reduce this. I think 25 goes into both of these. 25 goes into 125 5 times, and it goes into 625 25 times. And I could have reduced by more. And I see that I get a ratio of 1/5. Now, that doesn't mean the ratio is 1/5 unless that holds up again in another area. So I'm going to go ahead, take another term, and divide it by the term that comes before it. Notice I get 1/5 again. So this confirms for me, if I did this and checked between all the terms, that it's consistently 1/5, or you can look at it and see that each term is consistently being divided by 5. That yes, this is a geometric sequence. And we would recognize that the common ratio of this sequence is 1/5. Now, what we want to do is try to write the terms of a geometric sequence using only the first term and the common ratio. So we want to see if we can come up with a rule for the geometric sequence. So I'm going to look at the sequence we were just looking at. So this was 625. The next term was the first term times the ratio. Then remember, you'd get the next term by, again, multiplying by that ratio. So if instead of writing the third term as itself, I could write it as the second term, which looked like this, and then times 1/5. Then if I go on to get the next term, it would be the term before it, which now looks like this, times another 1/5. And that pattern would continue. So what I'm seeing here is I have my first term. Then this is my second term. And notice that it is my first term times 1/5, which was our ratio. This is my third term, which notice is my first term times my ratio again. This is my fourth term, and again it is the first term times the ratio times the ratio times the ratio. Okay? So I have my first term. My second term is my first term times the ratio. My third term is the first term times the ratio squared. My fourth term is the first term times the ratio to the third power. So notice that each of these have a specific setup where they're using the first term. They're multiplying it by the ratio. And the power that the ratio is raised to, notice, happens to be one less than the term number that you are at. So n minus 1. So that's going to be our rule for our geometric sequences, is going to be that to find any term an, we could use the first term a1 times the ratio to some power that's one less than what we're looking for. Okay? So then you can see here in example 2, they're giving us a sequence, and we are supposed to write a rule for this sequence. So I can see that my first term is 81. And then the question is, what is the ratio? So to find the ratio, I need to take a term. And they already told me it was geometric, so this should happen without, so I don't really have to check for that. And then this is my ratio, 108 divided by 81. Those are divisible by 3, I believe. So 27. And 108 divided by 3 would be 36. And then both of those things are divisible by 9. So I'd get 4 over 3. Okay. So 4 over 3 is my ratio. So to write my rule, have my nth term is equal to my first term, which I identified as 81, times the ratio, which is 4 over 3, to the power of n minus 1. So now somebody could go find any term in this sequence by plugging in the n value that they wanted. Like if they want the 10th term, they'll plug in 10. So in part B here, it says to find A11. Sorry, this should be written more like A11 with a subscript. This software just doesn't do subscripts well. So what I'm going to do then is take my rule and plug in 11. So to find A11, I'm going to do 81 times 4/3 to the 11 minus 1 power, or 81 times 4/3 to the 10th power. I don't expect you to do 4/3 to the 10th power by hand. I would use a calculator. So in our calculator, we would raise 4/3 to the 10th power times 81, and we would get that our 11th term is 1,438.376. I'm just going to stop the decimal there. Now, you might think, like, that doesn't make sense. Well, let's think about if it does make sense. First of all, it's bigger than where we ended, and the trend was that the numbers were getting larger, but not much larger. So it seems to make sense that by the time you got to the 11th term, you could be at 1,438. Secondly, you might think that it's weird that it has a decimal on it when none of these did. But eventually this might have a decimal on it, because think about your ratio being 4/3. So every time you go to get a new term, you're multiplying by 4 and dividing by 3. If that number is no longer divisible by 3, you're going to end up with a decimal. Okay? So it's okay that that happened. All right. The next problem says that one term in a geometric sequence is A2, which is 6, and the common ratio is 3. Write a rule for the nth term. Okay? So I'm just going to keep in mind what our rule is. So our goal is to get a form of this, so to know the ratio and to know the first term. Now, we know the ratio is 3, because they gave that to us in the problem. They didn't give us the first term in the problem. But you might think, well, it's not that hard to figure out. You had a first term, you timesed it by 3, and you got a second term, which they told you was 6. Therefore, the first term must have been 2. And that's correct. Now, if they don't give you such a simple term, like if they didn't give me the second term, if they gave me the 100th term, I might not want to figure out what times 3 all these different times through all these different spots to get back to the first term. So another way to do this would be to take your rule, but to write the rule for the second term because you know what it is. So if you plug in 2 for n, it would look like this. And then you know A2 is 6 because that was given in the problem. You don't know A1, you're looking for it. And then you know your ratio was 3, and now that's being raised to the first power. So you would have a smaller equation with a number times your first term equals another number, and you could finish solving for your first term. Again, here I'm not saying don't use the common sense way, but I'm saying that if it wasn't the second term that they gave you, it could have been harder to figure out. So there's my rule for this geometric sequence. All right, the last thing we're going to look at is if they gave us 2 separate terms of the sequence, how to find the rule for the nth term. So here they're telling us that the second term is negative 8, and the 7th term is negative 256. Okay. Now remember, we have that rule, and if we know the second term is negative 8, sorry about that, like we talked about last time, we could say, okay, then what happens when I plug in 2? So when I plug in 2, I get this. Okay? And remember that I know the second term is 8, so I can make this equation even a little bit nicer, or negative 8. So I'm going to have negative 8 equals A1 times r to the first power, because I plugged in 2 here. Okay? So then I can do the same thing for my 7th term, because the bummer is that equation is not solvable. It has an A and an R in it. So I'll see if my 7th term can help me out. So I have that the 7th term would be equal to the first term times r to the 7 minus 1 power. Then, if I plug in what I know, that the 7th term is negative 256. I don't know A1. I don't know R. And 7 minus 1 gives me the 6th power of R. Okay? So this kind of creates a system of equations with 2 unknowns. So what I'm going to try to do is substitute one equation into the other. So I'm going to solve one of these for A or for R, and then I'm going to go about doing that. So let's say that I rewrote this first equation in terms of A1. So I'd have negative 8 divided by R equals A1. And now I'm going to take that as the value of A1 and plug it into my second equation. So right here, instead of A1, I'm going to have a negative 8 over R plugged into this equation that has an R to the 6th power here and negative 256. And then I'm going to go about solving. So R and R to the 6th will cancel, leaving R to the 5th power. Then I'm going to divide both sides by negative 8. So I'm going to have R to the 5th power equals 32. Then I'm going to take the 5th root of each side. I don't need to include plus or minus because this is an odd indexed radical to get that R is equal to 2. Okay. So now I know that my ratio is equal to 2. So I'm going to have this part of my rule, but I'm still not going to have A1. So I'm going to go back to one of these equations that I wrote, probably the ones with the simpler power of R and simpler numbers, like this one that says negative 8 equals A1 times R to the 1. And I'm going to plug in my value of R. So negative 8 equals A1 times 2 to the first power. So negative 8 equals A1 times 2. Divide both sides by 2. So I have negative 4 equals A1. So now I know my first term is negative 4. My ratio is 2. And I have all the pieces of my rule that I need. So I'm going to write my final result of my rule. That AN is going to equal the first term, which is negative 4, times the ratio, which is 2, to the power of n minus 1. That's my rule. Now I want to emphasize the fact that notice we're not multiplying the negative 4 and the 2 together. The 2 has a power on it, the negative 4 doesn't. So if you plugged something in for n, you would always calculate the power of 2 first before you'd multiply by negative 4. So you don't want to combine those things together and try and call them negative 8. So these are the notes on geometric sequences. Okay, this technically goes with section 9.3 in your book. This is the homework that you'll be working on after the test on Friday. And then you guys can use the remainder of the time today checking certain homework problems and working on studying for your exam. And I will see you guys tomorrow.